compared to, this is a problem that wants you to put this into a series form, and we will eventually get into series, so this is just a quick reminder. I don't know if I want to go through the whole thing. Do you have that integral? You have it in your book, right? Trying to see if I can do this without doing the work. I mean, we could just guess, right? Multiple guess. So we have y is equal to x is a solution for this differential equation, and then they want us to use a reduction of order to write the form as an infinite series. Now, I don't quite remember the reduction of order formula, so maybe you guys can help me out here. P of x? All of this? And then do we have to divide out by x first to get p of x? So y double prime minus 1 y x. And so p of x is equal to 1 here in this case, right? So y1 is equal to x. So that's x. And then we have the integral of e to the negative 1. Integral of 1 is x, so this is just e to the negative x over x squared dx. Oh, okay, so positive 1. All right, so this is one of those things that you can't integrate. You can try, but you're not going to be able to. So what they want you to do is to write this in series form, and to basically to write this in series form. And so the way to do this is where series comes in handy, and that's the good news, is that you can use series to express this as a polynomial. The not so good news is that since a series is an infinite polynomial, you probably need to stop somewhere, and then that becomes just an approximation. So that's what's going to happen for us. Okay. You need to know the series for e to the x. And this is one of those things that you learned in Calc 2, and you thought, well, I'll never see that again. But here it comes, and this is something that you'll probably think about memorizing. And it's not hard to memorize. I think it's when you start doing the combinations of sines and cosines, that gets a little trickier, but you can still memorize those things. And if you just know this off the top of your head, it'll just become that much more handy when you guys are doing our work with series later on, chapter 6 or 7 or whatever it is. So that's what we have. That's this e to the x business over here. So the whole idea is that we can integrate polynomials easier than we can integrate stuff like exponential functions, and so that's what we're going to do. So we're going to keep the x out here. That's this x out here. And then we're going to integrate. Now, let me just, for the moment, write 1 over x squared, that x squared in the denominator, and then the e to the x business, I'll write out the first few terms. And then after that, we're going to distribute the 1 over x squared with what we have here and then integrate polynomials. So I still have that x outside. I have 1 over x squared plus 1 over x, and the x squared cancel. I have a constant, 1 over 2 factorial plus x over 3 factorial, and so on. Okay? So this is where the integral comes in. This is where we integrate term by term instead of integrating a complicated exponential. So this is going to be a negative 1 over x, right? X at a negative 2, you add 1, you divide by a negative 1, whatever. This is an ln function. This is a constant. And this is where it starts becoming the pattern. So x cubed over x squared, right? Squared over 2 times 3 factorial. And then if you want to go on, this is where the pattern happens, x cubed over 3 times 4 factorial, etc. Okay, and then now what's the only thing left is to multiply by x. So this is negative 1 plus x ln x plus 1/2 x squared plus x cubed over 2 times 3 factorial. And then good exercise to find the general n term here. So x to the n over, probably this is 1 less, so it's n minus 1 times n factorial. And then always end with a dot, 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 because it goes on forever, unless they specifically tell you to cut it off somewhere. So I hope one of those answers look like this. Yeah, the last one looks good, so we could select that. I can't select it for some reason. I don't. Oh, maybe it's past due, so I can't do it anymore. Okay. So we have that, and then we have conjecture, the interval definition for y, y2. Based on this, I have an ln x in here, and so that's never a good thing, right, for 0. And then, so I think I want to include everything on either left side or the right side of 0. So I think it's going to be on the right side because I can't have negative numbers here. So for that, the interval should be 0 to infinity. I don't have any other issues with any other finite numbers there, so I think I'm good to go all the way up to infinity. Okay. All right, so that's one problem. There was another problem in 4.4, and that'll get us going with doing one more problem with what's that method? Undetermined coefficients or something? Something like that, undetermined coefficients. So let's take a look at that. If Rick remembers the problem, do you remember number 6? Oh, 4.4? All right. So one of the things that I haven't done an example of yet was an example where the particular solution might be linearly dependent with one of the fundamental solutions. And if that happens, we need to be careful. I don't want to go through this whole thing, but I do want to go through finding the YP. Oh, this is even to the third power, right? Or third order. All right, so for the moment, let's ignore the right-hand side and look at this as if it was just a regular homogeneous differential equation. And what we're going to do is we're going to consider y triple prime minus 2y double prime plus y prime is equal to 0, a homogeneous differential equation. And then, you know, we find the, what's it called? Auxiliary, or what's it called? Some other, whatever. M cubed minus 2m squared plus m plus 0 is equal to 0. And so I think I can factor this by factoring out an m. And then I can even factor out that as a repeated root. Okay, so hopefully you're used to this by now. Without even thinking about it, I can say that my fundamental solutions would be x to the 0, e to the 0, sorry, e to the 0, and e to the first, or e to the 1 times x. And since it's repeated, I have an x e to the x. So that's my fundamental solution, and I will string that up later on as the solution to the homogeneous differential equation with a C1, C2, and C3. All right, that's the first part. Now the second part is to try to figure out, by the superposition principle, I could do this one by one, try to figure out what your variables or your parameters are, your coefficients are, undetermined coefficients. So the first one, I could just say this is equal to A, all right? And I could say y of P is equal to A, and that's going to be my particular solution. The derivative of that is all going to equal to 0. So when I plug those values in to the derivative, I'm going to get 0 is equal to A. So that means my A must equal to 0. All right. Now, I'm going to jump over to this one first, because the e to the x is going to give me some issues. So I'm going to have problems with this, so I'm going to avoid it for now. But if you can take a look at your fundamental solution and this particular solution that we're going to try to get, this particular solution is linearly dependent with one of our fundamental solutions. So we'll do that a little bit later, but now let's deal with this. So this one would be, I'm going to say b e to the 5x as my particular solution. So yp, I suppose we should call it different p's here, huh? P3 is equal to b times e to the 5x. So I need derivatives. I need up to 3 derivatives. Y P3 prime is equal to 5b e to the 5x, y p3 double prime is equal to 25 b e to the 5x, and then y p3 triple prime is equal to 125. Okay, so what I'm doing is I'm ignoring those other two terms and just focusing on that last term, and I will string this up together. The triple prime, 125 b e to the 5x minus 2 times y double prime, that's 25 b e to the 5x, plus y prime, which is 5 b e to the 5x, is equal to, again, ignoring these other ones, I'm just focused on 40 e to the 5x. And I'm really just interested in solving for b. I can factor out the e to the 5x and divide it all out, and then that's all gone. So what I have left is 125b minus 50b plus 5b is equal to 40. So b is equal to something that isn't too bad here. One half? Wow. Okay, I forgot to box my A. Not that it matters because it's 0, but let's box all the coefficients that we find. All right, now for the last one. This is where we have that issue where it's linearly dependent with a fundamental solution. And so if it's linearly dependent with a fundamental solution, usually our key is to just add on another x. So this would be c times x e to the x. But wait, I have another x there too. So x squared. So that's what's going to happen. If your e to the x matches a fundamental solution, then multiply it by x. And if it continues to have that problem, then keep multiplying by x until it's now linearly independent. Okay? Now I have to use, have to find 3 derivatives of this product, which I could do using Wolfram alpha, or we could just skip it. What do you want to do? Skip it? Huh? All right. You want the answer? I'll give you the answer. So we're assuming that cx squared e to the x is our solution, your yp. So I'll call that yp2 because that's the second term in the y equals 2. All right, so I'll call it yp2 of x is going to be some unknown constant c times x squared e to the x. And I want a bunch of derivatives of this thing. So I'm just going to say y p2 prime of x, y p2 double prime of x, y p3, or y p2 triple prime of x. So these are my derivatives. Not that I care about them, because I'm just going to take those values and then put it into the differential equation and then solve for it. So I'll do that by saying y p2 triple prime minus 2 times y p2 double prime. I need x. Plus y p2 prime okay, so that's going to be my left-hand side. That's my left-hand side. I'm going to see if I can get this to simplify a little bit. There, that's simplified. Okay. So I could take it from here. So using yp2 equals to c times x squared e to the x, I'm going to set this equal to cx squared. Oops. I'm going to set this equal to 24, negative 24 e to the x. Okay, and according to Wolfram alpha, this simplified to 2c e to the x is equal to negative 24 e to the x. And so c is going to equal to negative 12. And that should be my solution. Yeah? Okay. So, when I'm doing variation of parameters, I don't know if you guys do this all together, but since we have the superposition principle, I'm doing this one by one. Okay, so that's the first idea that could be brought up. And so I found it for 2, I found it for e to the 5x. Now, I saved this one for last because I knew I was going to have issues. My first idea here, my first thought, is that this needs to be represented by c times e to the x. Okay? Now, that's what we've done in the past, and we've had no issues there. But we have a problem in this particular problem because one of the fundamental solutions is linearly dependent with e to the x. So this is the stuff that I hadn't gone over yet. Okay? So when that happens, when you have one of your functions here being dependent with a fundamental solution, the easiest thing, the thing to do is to tack on another x in there. But then now I have that issue here also. So I can't do that. So tack on another x. And so that's how it becomes squared. Now, if I had x to the third here, then x squared, x to the third, I need to keep going until it is now linearly independent from all these other functions. Okay?
So those two are dependent from e to the x.
Well, just e to the x is dependent with e to the x.
And the other is dependent.
And x times e to the x is dependent on that. Yeah. So let me... So this is our first guess. No good, because it's dependent with one of these things. So our second guess is c times x e to the x. And this is also no good because it's the same thing as x e to the x down there. And so our last, or our next one would be so our next guess would be c times x squared e to the x. And then now I finally look down here, there's nothing like that down here, so this is good. And then you have to take the derivative once, twice, 3 times, because you need to put it back into the differential equation. And that's what I did using Mathematica, because that's a lot of work. Okay? All right, now that we have all this, your particular solution, we're not quite done yet. We have to actually write the particular solution. So yp is going to be, by the superposition principle, the sum of all these a. So I have a is equal to 0 of all these functions. A is equal to 0. I don't need to include that, or I can if I want. C is equal to negative 12. And then b, we found b to be 1/2. So remember, that's your particular solution. Now let's put it all together. Your total general solution is going to be the linear combination of your fundamental solutions. So C1 times 1 plus C2 times e to the x plus C3 times x e to the x plus your particular solution, negative 12x squared plus 1/2, negative 12x squared e to the x plus 1/2 e to the 5x. And from here, you're almost done. I'm not going to do it, but you would need to use your initial conditions to solve for C1, C2, and C3. You'll have 3 equations, 3 unknowns. You could do that. Say it again? Yes, because it's asking you, the conditions will be 1 less derivative than order. So this is 3rd order, we need 2 derivatives. The good news is that you're putting 0 in, if that's any consolation. Okay, questions? I know it's hard. It's going to get harder. Oh, I hope we did that correctly. I just kind of rushed through it. So because this is a constant, my first function is really just 1 times a times some unknown variable. So my first guess, if I ignore all this other stuff over here, and I just pretend that this is my differential equation, then my parameter that I'm going, my coefficient that I'm going to solve for is just a, since there's no other function involved. And if this is a, then I need 3 derivatives, 2 derivatives, and 1 derivative. So I need all these derivatives from a, which is all equal to 0, because it's constant to begin with. And then I would put in that yp, which is a constant. I would put that in here, and then I would try to solve for a. A is equal to 0, right? Oh, no, it's not. It's 2. Is it?
It's 0. Well, it's still 0.
0 equals 2 doesn't make sense. I'm a little worried about this now. Yeah, I'm afraid I went through that thing really quickly. No, that's a problem. Yeah, let's multiply it by x. Right? That's what we've been doing. All right. Thanks for asking that question, because now I have to come back and see what's going on here. Because you know what happens when we take derivatives of things, this thing, we get 0, and that's equal to 2. 0 is equal to 2 is a contradiction, and so that can't happen here. Something is going on. All right. A times x, yeah. Oh, yeah. Whoops. It is linearly dependent with this. Sorry. Let me highlight this and say we're going to go to the next page. And then that means that there's going to be some extra constants that need to go in here. So instead of 0, this is probably not going to be 0. Sorry about that. All right, we'll come back to this page and fill in these blanks. A is going to equal to 2. All right, well, we'll see. We'll see how it's going to look like. So let's, sorry about that, guys. All right, let's focus on this and remind ourselves that a fundamental solution has a 1 in it. So this 1 and this A makes it, or this constant makes it linearly independent. So instead of making this A, which is what I had done first, and then we got this bad contradiction, let's make it A times X. All right, now let's see if this will work out. So yp1 is equal to X, or I'm sorry, A times X. And we need 3 derivatives. Yp1 prime is equal to A, and then yp1 double prime is going to be 0, and so is the triple prime. Now let's put that into here. We got 0 minus 2 times 0 plus A. And then the AX doesn't go in there because we're not using y, so it's just y prime, y double prime, y triple prime is equal to 2. So A is equal to 2. So our y triple prime, y double prime, and our y single prime comes from that differential equation. And so A is equal to 2. All right, now let's go back and put 2 in there. Two. Yeah, 2x. Thanks. Okay. All right. It gets really messy. Any questions?
So because of those C numbers are dependent or independent, have to be one number has to be multiple of the other one.
If it's a multiple of the other one, like 1 and 2, yeah, they're like 24, negative 24 e to the x, and then e to the x. All you have to do is put a negative 24 in front of this e to the x, and then it becomes the same thing.
But if not, they are independent.
But if it's not, then it's independent. So, like e to the x squared, or I'm sorry, x squared e to the x is independent from all these other ones, because this is just e to the x, this is x e to the x, and that's independent from x squared e to the x.
Dx and dx are both independent.
Yeah, e to the x, x e to the x, and if you just had regular x, those are all linearly independent from each other. Because you can't just multiply by a constant.
So it has to be constant. It can be x and x.
No, it can't be x. X is a function. Okay? Wow. Sorry, sloppy. Okay, any questions? All right. The next section in your book is what's it called? It's called Undetermined Coefficients, the Annihilator Method. That sounds like a cool title. We're going to skip that. Because the method that we're using, it's called the superposition method, works pretty much the same way as the annihilator method. The annihilator method uses the differential operators, capital D, to help solve your problem, but it gives us the same results. So remember when we started talking about this, when we started this section, that we can only find particular solutions if our right-hand side were constants, were exponential functions, were sine and cosine functions. But we can't do it if it's ln x or 1 over x or or tangent x. And so that restriction is also the same restriction with the annihilator method. So it doesn't bias anything new. And so instead of going over that, we'll plan to skip over that particular section and jump to the next section where we can solve for particular solutions of functions that are more complicated than what we've been dealing with. Not that this is not complicated, because it sure was complicated. But the idea here is that we just string them together, and then that's how we work things out. But the next one we'll be able to answer questions where our right-hand side has a tangent x or something. ln x, 1 over x, some of those other weird things. All right. So we're going to jump to the next section. And the first page of the next section looks something like this. Now, I put this up here not for you to copy. But to say that I'm going to read through it really quickly, and whether you understand it or not doesn't matter, because what I'm going to do is I'm going to write down the summary of what this turns out to be. According to your textbook, if we're dealing with a second-order differential equation, linear, and it doesn't have to have constant coefficients anymore, what we're going to do is we're going to find a solution to the homogeneous differential equation, and then we're going to assume that our particular solution would be a linear combination of those fundamental solutions, but not quite a linear combination. A linear combination has constant times y1 plus a constant times y2. To find our particular solution, we're going to introduce two new functions, u1 and u2, where those will end up being the coefficients of y1 and y2, coefficients of your fundamental solution. Now what's going to happen when you do that is that you're going to take the derivative and the second derivative and put it back into the original equation. What's going to happen is that you're going to come up with images of the original differential equation. And those images of the original differential equation can be turned back into zeros, because they're just the particular the solution, the fundamental solutions. And so when you do that, you end up with a system of equations, two equations and two unknown functions that you're going to solve for. And we know y1 and y2, but we don't know what u1 is and u2 is. And not only that, but our equations, our two equations, have u1 prime and u2 prime. So we're going to solve for u1 prime and u2 prime, and then take the integral to solve for u1 and u2. Now, how we're going to do that is we're going to use some linear algebra where we use matrices. And the matrices that we're going to create are matrices with functions in it. So essentially, it's going to be the Wronskian. And our solution tells us that we're going to find the determinant of the Wronskian, original Wronskian, and the determinant of some modified Wronskian, where we change one of the columns into what the function is equal to on the other side. You with me so far? I know, you don't have to be with me. But if you are, then great. If not, read the book. Skim through this page at least, because this page, the content is really meticulously heavy. But like I said, it comes down to just streamlining the process. And the thing about the streamlined process is that when we come to a point in the process where we're asking you to do this, and you're going to ask why, well, the answer is on this meticulously heavy text part. It's only one page. So you're able to find the derivative of u1 and u2, but then you want the original u1 and u2, so you take the antiderivative of that, take the integral of that, and then you will have your particular solution. Ta-da! So that's the page. This is page 208 in your textbook. 209 on the top, it says, summary of method. Usually, it is not a good idea to memorize formulas in lieu of understanding a procedure. Usually. However, the foregoing procedure is too long and complicated to use each time we wish to solve a differential equation. In this case, it is more efficient to simplify the formulas into some manageable process. Okay? So here's where we are. This is a summary I just read. It's in our notes now, but it's also on page 209 in your textbook. So what we want to do, instead of going through that big process here, is your step-by-step process for solving for your unknown yp, your particular solution, in a little bit more concise form. And for this, we're going to stay with constant coefficients. So, variation of parameters, that's our new method that we're learning. And here's what you need to do. Whenever you're trying to solve for a differential equation, constant coefficients, that's non-homogeneous, where f is something more complicated than we've been doing, what we need to do first is to find a complementary solution, and finding the complementary solution gives us our fundamental solution, y1 and y2. Once you find that, y1 and y2, you're going to find the Wronskian of those two things. You know that it's not going to be 0 because they should be linearly independent. And then you're actually solving for a system of differential equations. And so you're going to need another modified Wronskian. So this is the modified Wronskian, the two modified Wronskians that I was talking about. Call it W1, where you're going to replace the first column, instead of the first column being y1 and y1 prime, you're going to replace it with 0 and f of x, and f of x is your right-hand side. So you'll construct that matrix, you'll find the determinant of that matrix, which you'll see, you know, one of them is going to be 0, and it's just going to be minus this thing. So that's an easy determinant to get. And then your y2 is the same thing, except you're replacing the second column with 0 and f of x. So those two modified Wronskians will each be divided by the original Wronskian to give you your solution, y prime, y1 prime, and y2 prime. Once you get that, you integrate each of those, because those are derivatives right now. You want the original u instead of u prime. You want the original u's by integrating. And once you do that, just put those in front of your y1 and y2 functions. And that is your particular solution. Okay? All right. Now, there's nothing to stop us from doing this with a problem that we've done before, where the fx is one of those nice functions like a polynomial, exponential, or a sine or a cosine. Or we could just jump to doing one that's more complicated already. Any preference? What do you want to do? Do something that we know the answer to already, or do a homework problem? Oh, this is not a quiz for our class. Quiz number 4. All right, this is in section 4.6, and with 10 minutes, I don't know if I could do a problem in 10 minutes. That's a cosine squared. All right, let's do the first one. All right, so cosine squared is definitely not one of those functions that we could do with the other technique. I keep forgetting the techniques. Auxiliary, no, the undetermined coefficients. Undetermined coefficients. So we can't do this with undetermined coefficients. We have to use our new technique, variation of parameters. Those are cool names, huh? I mean, annihilator method would have been cool. Maybe you should learn that. Okay, let's see if we can remember well, not remember, but let's see if we could follow through those steps and see if we can solve for this problem. So first, we need y double prime plus y equal to 0. We need the, what do you call it, the fundamental solution. The auxiliary equation, m squared plus 1 is equal to 0. So that's I, plus and minus I. That just becomes sine and cosine. Are we good? Fundamental solution. Cosine x, sine x. Okay? Skipped a few steps there, but Wronskian. So the first thing we want to do is find the Wronskian, and we'll call it W. So the Wronskian, if we say y1 is cosine and y2 is sine, the first row will be cosine and sine. The second row will be the derivatives. This is, I think, negative sine x and then positive cosine x. But you want the determinant of this. We got cosine squared minus negative sine squared, which is 1. That was nice. I guess I should write cosine squared x plus sine squared x is equal to 1. Okay?
How do you know that m squared is
Because m is equal to plus or minus I. We got complex conjugates, and so they have sines and cosines in them. All right, that is step, whatever step. I don't know if I numbered the steps, but it's one of the steps. All right, now we need the determinant of the modified Wronskian. Let's call this W1, where we replace the first column with 0 and the f of x function. Okay? And then everything else stays the same. Sine x, cosine x. Now, the determinant of this is 0 minus cosine squared x times sine x. All right, we'll keep that piece of information and then go on to W2. Another modified Wronskian. This time the first column stays the same as the original W. And the thing that we change is the second column. So that becomes 0 and f of x, which is cosine squared x. Okay, we good? All right, now that we have these W's, our U1 prime is equal to W1 divided by W, which is equal to W1 was equal to negative cosine squared x times sine x divided by 1. And if we want to obtain the original U1 function, we need to integrate this. So U1 is equal to the integral of negative cosine squared x sine x dx. I think this is just a U substitution, right? U is equal to cosine x. The derivative of that is negative sine x dx. So that's here. And then the negative would also cancel this out. And then you have u squared. Antiderivative of that is u cubed over 3. And then u is equal to cosine. So there. Did it all in your head. What was the answer again? 1/3 cosine cubed x. We'll do the plus c's later. Actually, we don't need the plus c's here because those get merged into those other constants. So this is u1. u2 prime is equal to w2 over w is equal to cosine cubed x over 1, which is cosine cubed x. And that, I think, is another not so hard integral. If you split this up, cosine squared and cosine. So in your head, you do this. You say, okay, cosine squared is 1 minus sine squared. We'll let u equal to sine squared. The derivative of that is cosine. That would cancel with the cosine dx. Take the integral, so it would be u minus u cubed over 3. U is equal to sine, so there you go. I don't know. Is this right? Are you guys doing it by hand? Wait, I have Mathematica. Of course, it's going to give me some other weird variation of this, but yeah, there's some other stuff going on here. Did you do it the way I said? Anybody want to second this? No? You don't know? 1 minus sine squared x times cosine x dx. U is equal to sine x. Du is cosine x dx. So this becomes u 1 minus u squared. Take the antiderivative. It'll be u minus 1/3 sine cubed, or 1/3 u cubed. I think this is right. All right. Okay. So now we have the fundamental solution up here, right? The cosine and the sine. So according to this, our particular solution is u1 y1 plus u2 y2. Let's see. u1 is 1/3 cosine cubed x, and then y1 is cosine x. So we're going to get cosine to the 4th in there. Plus u2 is sine x minus 1/3 sine cubed x. And we want to multiply that with y2, which is sine x. And then merge all this together. So I'm going to simplify this, but first I need to write the solution to the homogeneous differential equation. So C1 cosine x plus C2 sine x. Remember that when life used to be simple? Homogeneous, we'd be done. Now we need to add on the yp, and this looks like it's 1/3, and I'll say cosine to the 4th x. I'll just combine these two. And then I can distribute this sine x. So plus sine squared x plus minus 1/3 sine to the 4th x.
Cosine and sine squared x though. So you'll have you can factor that cosine squared x and sine squared to make it a 1.
Where? Here?
Yeah.
No, because this is the 4th and this is squared, so I can't do the factoring out completely. There are other ways to probably simplify this, where you might have a double, a triple angle formula and stuff. But I think in terms of this is the best you can do for now. Yeah. All right. So there's our first variation of parameters problem. 4-6. If you can get started, take a look at this to see how it works out. Actually, finish this and then type it in and see if you get the right answer. All right, good luck with this.